Before jumping into calculus material, we're first going to do some review of algebra and pre-calculus topics covered in sections 1.1 to 1.6 of the text. So calculus topics, the first one's going to be limits, is going to be covered in section 1.7. But in order to really understand these calculus topics that are going to be covered throughout the whole semester, we need to understand everything we've done previously in algebra and pre-calc. So the purpose of this video is to go over very generally some things that you should be comfortable doing, go into some specifics about very important things, and talk about things in general. So here's a list of things that I feel you should feel comfortable with before going into calculus material. Understanding what a function is, how to manipulate functions, and the idea of function notation. So that might mean doing algebra with functions, adding functions, subtracting functions, multiplying, dividing. Function composition, that is taking a function within a function. What is an even function and an odd function? And then dealing with inverses of functions. It's important to understand the graphs of functions and understand how to mess with functions. And we have a long list of those that we learned in a pre-calc course, covering everything from linear functions, exponential, logarithmic, trig, inverse trig, power, polynomial, and rational functions. And we need to be familiar with all of these as they're all going to pop up at one point or another in this course. Finally, there's going to be an idea of dominating functions. We're going to think a lot about end behavior of functions. And this idea is going to be immensely important when we think about limits in the next section or two. So let's dive into some material. First, I think it's important to have a library of parent functions. These are going to be some very general functions whose graphs and some information about the function should be immediately recognizable and replicated. I think a good example of this is the absolute value function, or maybe even better, the function y equals x squared. This seems to be a function that everybody can graph very, very quickly. It's a parabola. And from that graph, you can access a lot of different information about that function, and you're able to manipulate it in certain ways. We want to be able to do that with a whole bunch of functions. In fact, all the functions that we listed previously, we want to be able to do that with, and that can help us down the road. So these include linear functions. All lines are going to be needed in this course. We're going to be thinking about tangent lines in calculus, and in order to understand anything about that, we have to be very familiar and comfortable with lines in general. Absolute value is a good example of a function with some calculus properties we're going to look at. And then we have x squared is a great function we need. Square root of x is one that we need. X cubed, cubed root, those are all good. And then some more that we learned in pre-calc. What is an exponential function? What is a log function? 1 over x is a really interesting function that's going to be useful when we think about limits. 1 over x squared is another one. The greatest integer function right here is not as important, but it's a good example of something with discontinuities. And then we have the constant function as well. So all that information should be known and should be immediately recognizable. I want to just dive deep into one of these things. Let's look at the log function right here in a little bit more detail and explain what do I mean by have it be immediately recognizable. So if I give you a question about the function y equals natural log of x, and note that that is log base e of x, it might really help to know what that graph looks like. So it's very important to be able to graph that function accurately enough. And to me, accurately enough for log means that you have this general shape, and maybe you have this one specific point, which is true for all log functions, the point 1, 0. And that's true for all logs, no matter the base. It's important that we know that this function goes off to infinity on the right-hand side, and it approaches 0 as a vertical asymptote on the left-hand side. Another really important piece of information is the domain of this function is 0 to infinity, not including 0. That's a very important piece of information that is going to be used for the rest of your math careers. Also, in all of these, we have ideas of end behaviors. What happens to the ends of the functions? This one says that as x goes to infinity, we have that the function y also goes to infinity. And the other end behavior is not negative infinity in this case. It is as x gets closer and closer to 0, what happens to y is y goes to negative infinity. And these ideas, this idea of x approaching 0 or infinity, is the idea of a limit. And that's what we're going to understand later in this course, but it's good to have an idea of what these graphs look like. So when we talk about natural log, it's not confusing where it comes from. That's just one example of the functions. All of these should be recognizable, and you should be able to replicate that information quickly. So let's look at some more functions. These being the 6 trig functions, which are also going to be very important to understand all of these. Obviously, sine and cosine are the more important ones, tangent after that, but also knowing cosecant, secant, and cotangent is useful, though not as useful as sine, cosine, and tangent. So all the information we talked about before should be applicable here as well. Let's think about cosine and sine. It's important to know the basic function values for these off the top of your head. That is the pi over 2, pi, 3 pi over 2, and 2 pi. And then past that, knowing more information about the unit circle values is very useful as well. So what I like to do is I like to use the graph to remind myself of these values. You might have a different way of doing it, and that's totally fine. So sine, I know, starts at 0. It goes up to 1, back to 0, down to -1, and then to 0. And it keeps on repeating like that every 2 pi. Cosine, however, starts at 1, goes down to 0, to -1, back to 0, and then back up to 1, and repeats itself. So this red line is cosine, green line is sine. And that's just one period of sine and cosine. So the period here is the length of one cycle, and that is 2 pi. When we think about tangent instead, that's a different sort of one right there. Tangent has a period of pi, and one period is from -pi/2 to pi/2. And there are vertical asymptotes here because when we think about tangent, we have the trigonometric identity that tangent is equal to sine over cosine, which means that there are domain issues when cosine equals 0. And that means that we're going to have vertical asymptotes pop up. So the basic idea of what tangent looks like here is going to be kind of like a cubic function, sort of, at 0, and then goes to, approaches those asymptotes at -pi/2 and pi/2, and then repeats itself over and over and over again every pi. So here the length of one cycle is pi instead of 2 pi. Cosecant and secant are similar to sine and cosine. Cotangent is very similar to tangent, and that's because they are reciprocals of those. And we could go into a lot of detail about those graphs as well, but I want to focus on sine, cosine, and tangent more. So on top of all that, we should be familiar with inverses and their graphs. So we're going to look at two different inverses here. One is e to the x and natural log of x, and the other one's going to be the inverse trig functions on the next page. So first, let's think about e to the x and natural log. These are inverse functions, and they kind of cancel each other out algebraically. So that is if I take the function composition, natural log of e to the x, if I put e to the x inside of natural log, the natural log and the e sort of cancel each other out, and I'm left with just x. In the same way, if I go e to the natural log of x, put natural log inside of e to the x, they kind of cancel out and we're left with just x. That's the idea of a inverse function. We have the same idea that cubed root and x cubed are inverses as well because they cancel each other out. Graphically, what this means is that the inverse functions are the reflections of each other over the line y equals x. And this is the idea that all x and y's switch. That's what an inverse is doing. You're taking all the x's and y's and you're switching them. That's the same thing as reflecting over the line y equals x. So, for instance, in this graph, we have the special point for log that I pointed out earlier, 1, 0, is reflected to the point on exponentials, 0, 1, and that point is always there for exponentials as well. And every point is going to be the same thing there. You could take a point out here, and it's going to reflect where the x and the y's switch. So for instance, when you plug in e, this is going to be e natural log of e, which is the same as e comma 1, as natural log of e is just 1. And then the corresponding point here is 1 comma e. If I plug in 1, I should get a y value of e out. And every property of these graphs also reflects. So e to the x has a horizontal asymptote at y equals 0. E to the x approaches the line y equals 0 as you go to the left. The reflection over y equals x means that natural log has a vertical asymptote at x equals 0. Another thing we could say is that e to the x has domain negative infinity to infinity and a range 0 to infinity. And natural log has a domain 0 to infinity and a range negative infinity to infinity. The domain and the range switched. Domain has to do with x values, range with y values, and those all switch. So you can think about graphically, inverse functions have these properties. Algebraically, they cancel each other out, which allows us to be, it's very useful when solving equations or messing with things algebraically. The other example of inverse function is the inverse trig functions, and I wanted to show how one of those comes about, and that is arctangent. So when we think about tangent of theta, if we flip over the line y equals x, what would be the graph of arctangent? Well, what we would get is all of these horizontal asymptotes would now become vertical asymptotes. I did that backwards. All of the vertical asymptotes would become horizontal asymptotes. And that would happen at the values negative pi over 2, negative 3 pi over 2, pi over 2, 3 pi over 2. That corresponds to those values there on those vertical asymptotes. Then it's just like we take our paper and we're going to rotate it 90 degrees, and we get this graph out, these like tangents that are now extending horizontally instead of vertically. And that's what happens if I reflect that function over the line y equals x. The problem is that that is not a function. This is not a function because it does not pass the vertical line test. It hits the function an infinite amount of times, and that's not okay. So what we do instead to find the inverse function is we do it just for one period of the function. We look at just the period around 0 from negative pi over 2 to pi over 2. And that is our inverse tangent function. So when we're graphing this, we're just graphing one period of it. We have horizontal asymptotes at pi over 2, negative pi over 2, and there we go. There is a picture of arctangent of x, or also known as tan inverse of x. Let's make a little note here because it just needs to be said. Tan inverse is not the same thing as 1 over tangent. That's this notation, negative 1 power often means take the reciprocal. It also means inverse. It means inverse in this reason it's kind of ambiguous. That's why I'm going to refer to this as arctangent all the time instead of tan inverse. Please don't make this mistake. 1 over tangent already has a name. That's called cotangent of x. I should say that it is also important that we know all of these trig identities, as they're going to be very important. We'll do some examples to show some of those identities at work. The reason why I wanted to bring up arctangent specifically is because arctangent is a wonderful example that doesn't give enough credit of a function that has horizontal asymptotes, but it's not a rational function. And it comes up a lot more than you might think, the function arctangent. We're going to see it a lot, especially when we start doing antiderivatives. And you'll see it a lot in Calc 2 especially. All right, so now we have all of these graphs of functions. We kind of are able to deal with them. The big step in pre-calc that you take is you're able to take all of these functions and you're able to transform them and mess with them to get almost any kind of function you can deal with. You can add numbers, multiply by a negative, inside or outside of the function to get new functions. And the more comfortable you are with these function transformations, the better you can understand the functions that you're dealing with. And it goes beyond being able to plug in a function into a graphing calculator. Sure, that can give you maybe the graph of the function, but understanding the function transformations helps you understand what's going on with that function much, much better. And the more information you have, the better you're able to tackle the problem. So let's quickly look at the different kinds of function transformations we can have. I like to divide these up into transformations that happen outside of the function and ones that happen inside of the function. And the reason we can divide this up is because when we do stuff to the outside of the function, that is going to be messing with the y value of the function. You're adding 2 to every y value. You're multiplying every y value by 2. The x values are left unaffected. So that's going to change what happens vertically in the y direction to the function. So if I add or subtract a number to the outside of a function, that is going to be moving the function up or down 1 unit. So plus 2 is vertical shift up 2 units. F of x minus 2 is a vertical shift down 2 units. If I multiply by some number, that is going to be stretching or compressing the function by a certain factor. it's by 2, you stretch by a factor of 2. If you divide by 2, that's compressing by a factor of 2. And finally, if you do a negative on the outside, that's a reflection over the x-axis. And it is the x-axis, even though we said it's the y direction. Because note that if we reflect over the x-axis, the x value is left unaffected. It's the y value that has become the negative. Great. Just like that, if we do stuff to the inside of the function, we're affecting the x value. And this is the one that's a little bit tricky because it seems like everything that happens is the opposite of what we might want it to be. So for instance, if I have f of x plus 2 inside the parentheses, that's going to be a horizontal shift to the left 2 units. When you add 2, you go to the left when you're on the inside. And if you subtract 2, you go to the right. So that seems kind of backwards from what we're used to with the ones on the outside of the function. If we multiply by a factor of 2, that's actually making it smaller in the horizontal direction. It's kind of backwards. If you divide by 2, you're stretching it. And then the negative on the inside is a reflection over the y-axis. That one's not really opposite of what we want. So with all these in tow, we are now able to deal with any kind of function that you might want to deal with. So for example, we could deal with a function like y equals, let's use what we just did. How about negative arctangent of x plus 2. So that is, I know what my function arctangent looks like. Has some horizontal asymptotes. We just drew this on the previous page. And what I'm going to do with that is I am going to move it to the left 2 units. And then the negative on the outside is going to reflect it over the x-axis. So what's actually going to happen there is I'm going to get this graph out. Maybe I should extend these horizontal asymptotes. There's a picture of negative arctangent of x plus 2. And with that information, now you can get, you can understand maybe what we're asking better. If I'm asking for what happens to the function values as x goes to infinity, with that graph, you may be able to quickly understand that the answer is negative pi over 2. You'll be able to understand what is the x-intercept of that function, which may be very useful, especially when we start talking about derivatives, setting those equal to 0 and kind of how to deal with them. Just gives us more information. We're able to do this with almost any kind of function I can throw at you. All right. Let's think about polynomials for a little bit. Polynomial functions are maybe the most common function that we're going to deal with in this course or just in general because they're very nice and easy to deal with in general. Let's go over some terms that we're going to use a lot. So a polynomial function I should start out with is a bunch of powers of x multiplied by coefficients and then added together. A general polynomial is a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the terms in between a1x plus a naught. And note that this is non-zero. So this is a sub n is not 0. Otherwise, we could write it with just the n minus 1 term. N is called the degree of the polynomial. That's the largest power of x that we have. A sub n is the leading coefficient. It's the number attached to the highest power. And a naught is the constant coefficient. It's the thing that's just not attached to any x. We can find zeros of this polynomial by factoring. So for example, if you have the function 2x cubed minus 3x squared plus 1, that is a degree 3 polynomial. Leading coefficient is 2, constant coefficient is 1. If you factor that, it factors into x minus 1 squared, 2x plus 1. And if we set this equal to 0, we find the zeros of the polynomial of x equals 1 and 2x plus 1 equals 0. That's 2x equals negative 1. That's x equals negative 1 half. And there are zeros of our polynomial. And we can graph this polynomial pretty quickly just with that information and one more thing. So I'm going to graph, here's 1, here's -1, so here's -1/2. We know that we have a 0 at -1/2 and a 0 at 1. The multiplicity of the factors tells us the behavior of the function near the 0. So the multiplicity on the x minus 1 factor is the 2. The multiplicity on the 2x plus 1 factor is a 1, since there's nothing written there. And that number tells you if the function is going to bounce off the function or bounce off the x-axis or cross at that point. And we can use the two graphs, maybe to think about this as, here is x squared and x cubed. X squared is bouncing off the x-axis. X cubed is crossing. And if you have an even multiplicity, you're going to bounce, and an odd, you're going to cross. So that means that this graph is going to look either like this, cross at -1/2, bounce at 1, or cross and bounce this way. And we don't really know which one it is yet without one more piece of information, and that is the degree and the leading coefficient tell us about the end behaviors of the function. So there's a nice little chart that we can use for this. We're going to talk about the leading coefficient being positive and the leading coefficient being negative. And the degree being even or odd. So if the degree is even, we think about x squared, the end behaviors are going to go in the same direction. And if the leading coefficient is positive, they're both going to go up. If it's negative, they're both going to go down. And I think it's okay to think about an example like x squared or negative x squared. It's a nice simple function to look back at. If n is odd, they go in different directions. So if the leading coefficient is positive, on the right it goes up, on the left it goes down, and backwards for if the leading coefficient is negative. And we can use maybe x cubed and negative x cubed as examples here. So our function, 2x cubed minus 3x squared plus 1, has a positive leading coefficient and a degree that is odd. So we should have this third case, n odd, leading coefficient positive, which means that this yellow graph that I did before was indeed the picture of the function. And we can get that very quickly just from that information. And what's going to be most important to us is the end behavior itself. Does the function approach positive infinity or negative infinity based on the leading coefficient and the degree? Another very common function we're going to look at is a rational function. A rational function is just going to be any polynomial over any other polynomial. So here's a very quick rundown of some facts about rational functions. If there is a common factor in between both of those functions, then there is a hole in the graph. Let's do a very quick example of that. So if you have x plus 1 over x minus 3, x minus 2, x minus 3, and actually let's get rid of the x minus 2. Let's just do over x minus 3. Here's a rational function, but note that there is a common factor in the top and the bottom. So we can think about this as the same thing as x plus 1. And that's almost true if we graph the function x plus 1. That's a linear function, slope of 1, y-intercept of 1. Here's x plus 1. This is the same, except there is a hole at x equals 3. X equals 3 because of the x minus 3 there. So if you graph the hole there, that is now a picture of x plus 1, x minus 3 over x minus 3. And that's going to be a kind of function that we're going to look at very early in the calculus when we're thinking about limits and how those two functions relate. Some other important facts about rational functions. If you set the numerator equal to 0, you get the zeros or the x-intercepts of the function. If you set the denominator equal to 0, you get vertical asymptotes of the function. And then again, the idea of end behavior is very important when we're thinking about these functions. So this is the idea of a horizontal asymptote. And we get the idea of the horizontal asymptote by looking at the degrees of the top and the bottom. If the degree of the top is bigger than the bottom, then we say there's no horizontal asymptote. That means that y goes to infinity, or we'll say positive and negative infinity as x goes to infinity. It doesn't approach some number. If the degree of the bottom is bigger than the top, then there is a horizontal asymptote, and it happens at y equals 0. If the degree is the same on the top and the bottom, then there's a horizontal asymptote at y equals the ratio of the leading coefficients. So example, if you have 2x squared plus 1 over 3x squared plus 2x plus 3, the horizontal asymptote here would be at y equals 2/3, because the degree is the same on the top and the bottom, and that's the ratio of the leading coefficients. All right, the last little topic here is the idea of dominance in functions. And that's something we just kind of covered in that last page, is the idea of the bottom being bigger than the top has to do with dominance. So the first idea is that polynomial functions dominate polynomial functions of smaller degree. So for example, 2x to the 5th is a much larger function than x to the 4th as x goes to infinity. But I could say that 2x to the 4th is not much larger than x to the 4th. Because of the same degree, we're not going to say that it gets much larger, but 2x to the 5th is. So if you have a higher degree, then that's going to be much larger. And what that means is, if I look at 2x to the 5th over x to the 4th, I know that as x goes to infinity, y is also going to go to infinity because it's the 2x to the 5th that dominates. The x to the 4th doesn't really even mean anything. Or for instance, if I have x to the 4th over 2x to the 5th, I know as x goes to infinity, y is going to go to 0 because the 2x to the 5th will dominate. Another way to think about it is if you have a function like 2x to the 5th plus x to the 4th, the x to the 5th won't really make a difference. You can look at just the 2x, or the x to the 4th won't make a difference. You can look at just at 2x to the 5th to answer some questions about end behavior as well. The one that's going to come into play a lot for us is the idea of that exponential functions dominate polynomial functions. If you have any exponential function like e to the x, that's going to be much larger than x to the 20th or any polynomial function as x goes to infinity. So that means that if you have e to the x over x to the 20, as x goes to infinity, this is going to look like just e to the x. because x to the 20 compared to e to the x is just much, much smaller. Likewise, x to the 20 over e to the x will basically just look like 1 over e to the x as x goes to infinity. In the grand scheme of things, as x gets really, really big, that x to the 20 is not making a difference in that function. So you could answer questions about this weird function by just looking at the dominating term. Lastly, exponential functions dominate exponential functions with a smaller base. So 3 to the x is much larger than 2 to the x. So we could say as x goes to infinity here, this function is going to blow up to positive infinity because the 3 to the x is bigger. Or the other way around. This will go to 0 if it's on the bottom. This is something that we're going to investigate a lot in the first chapter of this course, looking at limits. This is basically what we're doing is limits at the moment. All right, big thing to remember is the first two especially, but this exponential function one we're going to look at a lot in this course. All right, finally, there's a little important note I wanted to say, and this is true for each and every student, including myself when I was in your position. There is way more things to go over than what I did in this video. It would take literally years to go over all that material, and that's why you had to do the prereqs for this course to get into this course. Part of me knows that you need to have all of that information in order to understand calculus, but I also know that each and every student has gaps in their knowledge. For me, I was not comfortable with logs when I was in Calculus 1. It just never really made sense. I was never really comfortable with that material. And it wasn't okay that I wasn't, it messed me up and I had to fill that gap in my knowledge. You have your own personal gaps in your knowledge, and they may not be anything that I went over in this video. It might be something else related to it. And it's your responsibility to fill those gaps in your knowledge before they can cost you in a Calc 1 setting. And note that that may not be able to occur before we jump into Calc 1 material. It might be as we're doing material. But please do try to look for those and correct them. I will say that many mistakes, if not most mistakes in a calculus course, really don't have anything to do with calculus themselves. It has to do with everything we just talked about, algebra errors, pre-calculus errors, and background knowledge that we need beforehand. Most students actually understand the calculus things that we have to do pretty easily. So if at any point you need help with something from a previous course or class, it is expected that you will have to have some help at some point. So please reach out and ask for the help. Everyone has gaps in their knowledge. It's expected. It's just our responsibility to fill those. In the next video, we'll go over lots of different practice problems to get more familiar and caught up with the pre-calculus material.